Hello, my name is Daniel. I'm in my office today to verify the configuration of this 18 gigahertz radio that my installation crew is going to deploy in the field tomorrow. Now, my technical team's already configured this radio's radio settings like the transmit output power, the channel bandwidth, and also the Ethernet settings like the VLANs and the IP addresses. But what I want to verify is that the radio configurations they made in the GUI is what this radio is actually transmitting. Now, you might ask, why do I want to do that? Oftentimes, an installation crew goes out on site, they climb the tower, they might have difficulty with the alignment. One of the first things they're going to blame is the radios. Do we know they're good? And historically, it's been very difficult for the average installation team to verify the configuration of the radio, verify that's actually operating. So what I can do is I can provide peace of mind to my installation team that if they do have issues with the alignment, that they don't have to look at the radios and wonder, is it actually transmitting at 10 dBm? So the first thing the way I'm gonna do that today is I'm gonna use my SAF Technica Spectrum Compact. This model is between 17 gigahertz and 24.3 gigahertz. And the other important thing on this label is it does have a max input of 0 dBm. Now, why do I point that out? The radio is transmitting at 10 dBm, so I will damage the Spectrum Compact if I feed it a 10 dBm signal. So the first thing I'm gonna do is I'm gonna pull out my attenuators from this kit. Now there's three 20 dB attenuators here to provide a total of 60 dB of attenuation. This will provide a signal to my Spectrum Compact that it can read and measure without damaging the unit itself. The next thing I'll do is I'll take out my waveguide adapter for 18 gigahertz. Note that this does have a rectangular flange, just like the radio, and it's very important that I match the flanges together when I mate them. If I cross-polarize them, I'll get a much weaker signal on my Spectrum Compact, and that could point to an issue. The last thing I'll do is I'll grab the ruggedized SMA cable to connect everything together. So the first step is to attach the waveguide adapter to the radio. Now with the thumb screws on the waveguide adapter, it makes a very quick job instead of having to use a screwdriver. Next thing I'll do is I'll attach one of the attenuators to the waveguide adapter. And I will attach one to the Spectrum Compact. Last thing, I'll go ahead and connect everything together with the SMA cable. And I can now safely power up my radio. Alright, so we'll go ahead and turn on the Spectrum Compact. The first thing I'm going to do is I'm going to go ahead and set the offset for the attenuators. Now, when I put in the 60 dB of offset into the Spectrum Compact, what it does is adjust the vertical axis to account for the fact there's 60 dB of attenuation in the signal, or the cable. The next thing I'll go ahead and do is set the frequency of the transmitter. This radio is transmitting at 17.92 gigahertz, so we'll go ahead and put that in. And the next thing I'll go and do is adjust the span. Right now it's got a span of 1 gigahertz on the field, but I'll go ahead and set that to a minimum span of 100 megahertz to go ahead and give me a much clearer picture of the signal. Last thing I'll go ahead and do is set the average. What this will do is it'll take 8 averages of 8 sweeps of the signal and average them together to give me a much cleaner picture of what the radio is actually transmitting. Now, before I move forward, there's a couple things I can tell about my radio. One, the signal is symmetrical. The amplitude is even. I have no spikes, no notches in the signal, and that's a clear picture that the radio transmitter is operating correctly. If I saw spikes in the field outside of the channel, if I saw notches in the signal, or a non-symmetrical signal, that could tell me that the transmitter is damaged and should not be deployed in the field. The next thing I'll go ahead and do though is I'll check, what is the transmit output power of this radio. So to do that, I'll go to power and band. I'll select a 40 megahertz wide channel, and we'll go ahead and go back to the main screen. So what I can see here is this radio is transmitting at 10 dBm. It's actually transmitting a little bit hotter, somewhere between 10 and 11 dBm. So that tells me the radio is operating correctly. My installation crew can expect in the field to be able to hit their target alignment. The last thing I'll go ahead and do is I'll go ahead and hit save. What this will do is it will save to my Spectrum Compact unit this graph that can further diagnose on the Spectrum Compact management software on the computer, and I can also refer to in case I have any questions about, is this radio actually was it operating correctly on the bench in the future? In case this radio ever comes back from the field. So what I've done today is I've verified that the radio is transmitting at 17.92 gigahertz. I've verified that the channel bandwidth is 40 megahertz. I've also verified that the transmitter is operating correctly at a transmit output power of 10 dBm. So now my installation crew can be rest assured that this radio is operating correctly when they go to deploy tomorrow in the field. Thank you.